Now, as with the geometric random variable, we have a bunch of nice formulas that we can derive for expected value, variance, etc. So keep in mind, again, your cumulative distribution function, we have nothing concise when r is not equal to 1, right, when we're not dealing with the geometric. And for that reason, there's nothing concise for a survival function either. Notice the similarity, though, in the expected value, the variance, and the moment generating function. So for the expected value for the geometric, you just have a 1 over p. In the negative binomial case, you have r over p. The variance for your geometric is just q over p squared. For the negative binomial, you have r times q with a p squared. Right? So basically, you're just multiplying the geometric random variable expectation and variances by r to get the associated one for the negative binomial. And in terms of the moment generating function, you end up with, inside the parentheses here, this is just the moment generating function for the geometric random variable. And then you raise that to the r to get the moment generating function for the negative binomial. So you'll notice that there's a little bit of a difference with the series that you end up having when you do some of these computations. So like as a quick reminder, right, our series, when we were adding up x less than or equal to 5, involved not only successive powers of 0.89, but also these kind of special chooses, right? There is a special geometric series associated to the negative binomial random variable, and it comes out, it essentially looks like this. Here's the shortcut for it. If you have x minus 1, r minus 1, a to the x minus r, you can simplify this as 1 over 1 minus a raised to the r power. All right, so I think you have a reading quiz, or maybe a reading that sort of goes over where this thing comes from. It's essentially, I think, a Maclaurin series expansion of this function, and an example or two of where you could use this. All right, so let's look over another example. So suppose 4 out of every 15 cereal boxes contains a secret decoder ring. Jason, who loves the cereal, decides to just keep eating cereal until he gets a decoder ring for each of his 4 sisters. How many cereal boxes without a decoder ring do we expect Jason has to eat before he accomplishes this task? All right, so this is kind of interesting language here. We're asking about how many cereal boxes without a decoder ring do we expect Jason has to eat. So first, let's think about what kind of random variable models this well. So each cereal box is either going to contain a decoder ring or not. So we can think of eating or opening a cereal box as a Bernoulli trial, with success being essentially having a decoder ring. All right, and then we know that the probability of success in this case is going to be 4 out of 15. Now, Jason has 4 sisters, so we're not looking for the first success or the second success. He's just going to keep eating cereal until he gets 4 successes, right? So the R value is going to be 4. And again, it sort of has this geometric negative binomial flavor to it, that you keep repeating the Bernoulli trial until you achieve the number of successes that you want. Right, so X, which is going to count number of repetitions necessary to get 4 decoder rings, X is going to have a negative binomial random variable with R equaling 4 and a p-value equaling 4 out of 15. Okay, so we'll keep this in mind. Now, here's the tricky bit. When we actually ask about our expectation, what we're asking about is the number of cereal boxes without a decoder ring. So this is kind of like the number of failures we have to endure in order for us to achieve that 4th success. Okay? So technically, we're not working with X. We're working with a different random variable. But it kind of depends on X, right? So let's define Y to be the number of cereal boxes without a decoder ring. Necessary to get 4. All right, then essentially, and here's the key, right? Y is just going to be X minus the successful cereal boxes. So this X is the total number of cereal boxes it takes, but 4 of them were successes. So if we only want the failing boxes, we can just think of Y as X minus 4. Okay? So with that in mind, what we're interested in fundamentally is the expected value, right? We've got expectation going on here. The expected value of Y. This is what we want to find. All right, so I'm going to create a little space here so we can finish this off. We want the expected value of Y, which is equal to the expected value of X minus 4. And using the linearity of our expectation operator, this is the expected value of X minus 4. Now, keeping in mind that X is negative binomial, with R equaling 4 and P equaling 4 out of 15, the expected value of X is going to be R over P, which in our case is 4 over 4/15. And the 15 can swing up to the top. The 4s will cancel. This will be 15 minus 4. So this should take, as an expected value, about 11 boxes without a decoder ring. To get 4. Okay, now it actually, this value here, the 15, this is the total number of serial boxes it takes to get 4 decoder rings. So the number of failing boxes, or boxes without a decoder rings, would be 4 less, or 11. Okay. The last question here asks, what's the coefficient of variation for this random variable? So let me create some space on the other side, and we'll talk about this. So we already found that the expected value of Y is equal to 11. What we want is the coefficient of variation. And from the reading, we remember that this is defined as the variance of our random variable square rooted, so essentially the standard deviation of the random variable over the expected value. All right, so we already know the bottom is going to be 11. We'll know we'll take a square root. What we need to know is what's the variance of Y. So using our property here that Y is essentially just X minus 4 in terms of a random variable, keep in mind that our general formula, all right, if you take a linear combination of a random variable and look at its variance, this becomes a squared variance of x. Now, in our case, a is equal to 1 and b is equal to negative 4. So this ends up just being equal to the variance of x. And again, since x is negative binomial, with r equaling 4 and p equaling 4 out of 15, right, we can use our formula to figure this out. So this would be rq over p squared. So this is going to be 4 times 11 out of 15 over 4 out of 15 squared. So this whole thing is going to simplify to 165 over 4, which is approximately 41.25. All right. So that's the variance of y. And so we would put the square root of 41.25 in here. And so our coefficient of variation as a final answer, this will be about 0.58 let's call it 3.9. All right, so this would be the coefficient of variation. And this is the coefficient of variation for the number of cereal boxes without a decoder ring that Jason would have to eat in order to find 4 decoder rings. Okay? All right, let's consider our final example. So we have Robin Hood plans to open an archery school, but only wants to accept the best. So each week he holds a qualifying competition where archers are allowed 3 shots at a target, and Robin Hood's going to keep track week by week of which archers hit the bullseye. All right, so to enter Robin's Academy, you have to hit at least 1 bullseye in 6 qualifying competitions, right? So you'll require at least 6 weeks in order to get into the Academy. And for those 6 weeks, you'll have to hit a bullseye at least once. Right, so assume that for each shot, you hit a bullseye 15% of the time. What we want to know is what is the probability that it takes you more than 7 qualifying competitions to get accepted to this academy. And then we're also going to take a look at the expected value and the variance and look at a range of scores, which is 2 standard deviations away from the expected value. So let's start with number 1. First of all, let's kind of think about how this actually works. So it's broken into 2 pieces here. The first piece is the fact that in order to get into Robin Hood's Academy, you have to hit a bullseye in 6 weeks, right? 6 of however many weeks it takes. So you're just going to keep going to these competitions until you hit a bullseye in 6 of them. All right, and Robin Hood keeps a record. So it's following this general idea of a negative binomial setup where we just keep showing up at the competition, right? Each competition ends up being the Bernoulli trial, and a success is you hit at least 1 bullseye using your 3 shots. Okay, so we'll stop. We're accepted into the academy when we finally have our 6th qualifying competition where we hit a bullseye. All right, so let's keep track of what's going on here. So let's let X count the number of competitions required to enter the academy. Okay? And we're noting here that X sort of has the flavor of a negative binomial random variable. We know that it requires 6 qualifying competitions, so our R value here is going to be 6, and then P is going to be the probability of hitting at least 1 bullseye. Okay? And in fact, I'm going to shade that in red because this is sort of the second part that we need to consider. Right? Every week he holds a qualifying competition. Each archer gets 3 shots at a target, and we assume that for each shot you hit the bullseye 15% of the time. All right, so in determining P, we're going to have to use this type of idea. All right. Now, notice in this case, like let's model this red part with Y. Y is going to count the number of bullseyes in 3 shots. Now we have a fixed number of shots that we're taking. So if we think about what kind of random variable, since we have a fixed number of repetitions and we have a probability of success 0.15, Y is actually going to be binomial, where n is equal to 3 and p is equal to 0.15, right? And in this case, our success is defined as hitting a bullseye. So what we want to know is what's the probability of hitting at least 1 bullseye. So probability that y is going to be greater than or equal to 1. And the easier way to do this is to do 1 minus the probability that y is equal to 0. So this would be 1 minus 0 successes. So this would be 0.85 to the third. And this is approximately 0.3859, we'll call it. All right. This is going to be our parameter right? This probability we just computed is going to be the parameter little p in our negative binomial distribution. Okay? So let me create some space over here. We have x negative binomial, r is equal to 6, p is equal to 0.3859, right? And x is counting the number of competitions required to enter the academy. All right, so we've seen examples like this before. We have a layering of random variables. We've got the main random variable of interest, which is negative binomial, but the parameter little p for that main random variable of interest, we had to compute via another random variable, which was actually binomial. Okay, so it's kind of a complicated setup, but we're starting to understand this. Now what we want to know is what's the probability it takes you more than 7 qualifying competitions to access the academy? Now keep in mind this is a question about the random variable x, right? So what's the probability the number of competitions is more than 7, so strictly greater than 7. All right, so let's pull off a little bit of space here. Problem 1 is essentially asking what's the probability that x is greater than 7, or in other words, what's the probability x is greater than or equal to 8. So we would think about this in terms of f of 8 plus f of 9 plus f of 10 plus etc., etc. And technically we have an infinite summation here. But since it's not very common to memorize that negative binomial series, right, the easier way to approach this would just to be the 1 minus trick. All right? And keeping in mind that the space of x starts at 6 and then counts its way out, this would be 1 minus f of 6 and f of 7 taken together. Right? So now using the negative binomial PMF, we would have 1 minus, our x value in this case is 6, so x minus 1 would be 5. R minus 1 is also 5, so you have 5 choose 5. Our probability of success, I'm going to leave this as little, well, I guess maybe I won't. So 0.3859 to the 6th power. And then the Q, or the probability of failure, would be to the 0. So I'm not going to add that in. And then in the next one, I would have an x value of 7. So this would be 6 choose 5, the 0.3859 to the 6th times, so this would be 0.6141 to the 1st. All right, and now we can jump to our calculator to compute this. So this is approximately 0.9845. So it's a pretty good chance that you're going to have to go to at least 8 or more competitions in order to get into Robin Hood's Academy. All right, based on your shooting percentage of 15% bullseye in any given try. Okay, to finish this problem, we just want to look at the range of scores represented by 2 standard deviations from the mean in either direction. So remember that the mean and the expected value are essentially the same. So we want to know what's the expected value of x. And then your standard deviation is just the square root of your variance. So we're going to look at the square root of the variance of x. So we'll compute each one of these using our formulas. Remember, this is, expected value of x is r over p. So this would be 6 over 0.3859. So this is approximately equal to 15.5. And then the variance of x, this is RQ over P squared. So this would be 6 times, what do we get, 0.6141 over 0.3859 squared. So this is about 24.74. So then the standard deviation here would be the square root of that. So this is approximately 4.97. Okay. So what we want to do is look at the range of scores that represent the number of competitions necessary for us to enter the academy. So specifically, the usual range of scores are 2 standard deviations from the mean. So if our mean is 15.5 on the lower end, we would expect 15.55 minus 2 times our 4.97. So this gives us something about 5.6. And on the upper end, we would go 2 standard deviations in the other direction. So this would be 15.55 plus 2 times 4.97. And this is approximately 25.5. Okay. So, in conclusion, sort of the usual range of scores, or the range of scores that people would typically report in statistics class, would be anywhere between 5.6 and 25.5. Now, I wholly realize here that 5.6 doesn't make sense because you would need at least 6 to get into the academy. So again, this is sort of loosely interpreted. You would think anywhere from 6 to somewhere around 25 would be a reasonable number of competitions you'd have to attempt in order to get into the academy.